Hi folks, we are from E6 Data. I'm Mrinal and this is Arush. So the agenda for today's talk is we will walk through about, we'll give a walkthrough of our stream processing engine and we'll talk about the first principles involved in building one from yourself. So a bit more about E6 Data to put everything in context is that we are a Lakehouse compute engine and we're built for the next generation workload. So we build compute engines for querying, for ingesting, and all of the other things that a company may need for its data analytics need. Right? Specifically, we fit in these places. So like we have a compute engine for ingesting, which sits between your data sources and between the lakehouse you want to adopt. So we can get your data from database CDC, from clickstream events, and then put it into Iceberg. And then we have another compute engine which helps you actually run queries on top of these, on top of the lakehouse ecosystem. Right? So you can do analytics queries, like you can power dashboards, all of it using this compute engine. So, so specifically, this talk is focused about the first part of this whole data flow, which is the real-time ingest engine, right? Why did we had to build it, and how did we exactly go about doing that? So shout out to the ingestion team. It's like it was a work of all of us over the last few months. So yeah, let's start with the why, right? So explorations with our customers highlighted a missing piece, right? We already had our query compute engine set, and a lot of customers wanted to adopt that. But often scaling customers don't have their data sorted in one place, right? It's all over the place. Some of it is in Postgres, some of it is in CSV files, and they're like duct taping all of that together and trying to do things on top of that, right? As Shubham also said, like adoption for Lakehouse is low and Iceberg is relatively a new player. So for instance, one of the customers who wanted to use E6 data had their data scattered all over, right? So they needed to, so we realized that the missing piece that we need to solve for this bottom layer, right? We need to help people move to the Lakehouse and in a way that is easy and intuitive for them, right? So another conversation that we had was around a company which had their data pipeline sorted and figured out, but ingesting and querying at scale is a very, very expensive problem, right? So even if you have a team dedicated and you're using some off the shelf solution, maybe you're hitting into scaling challenges, or like, you know, the money spent in doing all of this is too much, right? So, so all these conversations with customers, like, they gave some clear indication that there is a missing piece, that people want to move from existing scattered solution that they have to something that is governable, something which can work at scale, like, and there is a space for a solution, right? So we arrived at this equation basically, that people at the end want to do real-time querying. And for that, you need a processing system, an ingest system, and a query system, right? So we've already built a query compute engine, and the missing pieces are process and ingest. So we decided as a company to invest time in this entire process of building a process and ingest layer. Right? So this is the problem that we're trying to solve, like enable real-time query with the benefit of Lakehouse. Right? But if we dig deeper into this problem, right, processing, ingesting, and querying at, you know, real-time, like order of time at a scale is a very, very hard problem. There are existing solutions, but there's no one solution that fits this entire stack. Right? You can use Flink and other systems, but then you need to invest money and time into managing your Flink pipelines and all that. And there's no status quo solution as well. That's why you see a lot of startups and companies emerging out into the space of ingestion and writing into Lakehouse, right? So naturally, we decided that we're in the business of building compute engines, we have to do this, especially because building a query compute engine and building an ingest compute engine like gives us the flexibility to integrate them tightly as well, right? So this talk is focused on this middle piece, like how did we actually build this bit, right? And the thing to focus is there, we want to build the system in a Lakehouse native fashion, not just writing it into any other sync. Right. So now we'll talk a bit about the challenges that we initially identified and like how we went about this. Arush will talk about that.
Hello, wonderful people of the data world. Yeah. So I think Mrinal has very well painted a picture on why there is a need for an ingestion solution in the market right now. I think we're on the same page about that. So then, what's the next big question? Is the how? How do we handle these things? And I'd like to start this off with the challenges that everyone who is trying to build a stream processing engine is almost certain to face. So, okay. Yeah, so the problem arises with this notion of having a stream of data instead of having a data that already persists in a durable state store. So think of it like data at rest versus data that is in a streaming fashion. With data at rest, you would be pretty aware about the exact boundaries that you need to play with, and that I think allows for a much smarter optimization of resources and just managing the overall workload. And on top of that, I think it's relatively very easy to handle the engine uptime, because you can have a fair idea on what time would be required to execute a certain task, and you can have your engine running up for that amount of time, and then once you're done with the things, you go into a downtime state. But with streaming, the data is an indefinite stream of data. It never stops. So the problem is to have an engine that runs at all times, is able to handle data at a petabyte scale, is highly elastic in terms of being able to scale up up the compute power, and all of this is very important because we are focused on having a cloud deployment, and you all know cloud environments are very costly. So then, now we know that unbounded data brings in a different set of challenges. So one issue that I think is a big task for us right now as well is how do we figure out what kind of capacity we need, because in a streaming data thing, you never know what kind of rate of events you're going to be handling at any point of time. So the engine requires almost always to have more capacity than the current throughput of events, just in case if the rate of events increases, you don't have a choke point even before the pipeline starts, and at every stage of the pipeline. And what is very important on top of all of this is having an available system, available at all times, is durable, because in a lakehouse format or any persistent state store, you can always in case of a failure, you can always reload data because it is already persistent in a durable state store. But in streaming, if you are not able to handle things at a given point of time, you actually end up losing data, which is something that we totally don't want. So you have to have provision for a durable system, which would require managing state at every layer of the engine. So we'll be talking about some core components of an engine and how they manage state at every level. So then, how do we deal with unboundedness of data? It's a very logical solution if you come to think of it. It's like having a logical bound over the unbounded indefinite stream, and you play within bounds at a time. So we have concepts of windowing and watermarking, which are essential to be able to play with a streaming data thing. Uh, Windowing is like there are multiple ways of handling data windows. There can be a use case where you handle data. So you're interested in handling the recent 5 minutes of data, as in the last 5 minutes of data that the engine has ingested. So there's a concept of sliding window, which you can set up a time limit that after this much time it slides by 5 windows, 5 minutes ahead. There can be tumbling windows where the next window starts at a point where the first window ends. So we have all sorts of those things, and on top of that, we have watermarking, which is, I believe, all the streaming engines right now also have. Watermarking is about using timestamps in the data and striking a balance between how much how much you can wait for data, so what you have essentially makes sense. As in, so say that there's a stream of events coming in with timestamps, and you have to figure out how after, okay, I've witnessed an event with this timestamp, I'm not going to allow an event that was before this timestamp. It's called lateness allowance. So if you keep waiting for too long, your analytics would be stale. If you jump ahead very quickly, your results would not be complete. So to have completeness in the data but still have enough compute performance, we have to strike a balance somewhere. And I think it's ideal to have that balance differently for different use cases. So let's understand the state of the art solution that is widely adopted in the industry, which is Apache Flink. I think Mrinal can talk about it.
Yeah, so now we know that the challenges of dealing with streaming data are different than dealing with data at rest, because unboundedness and like you as a system need to give first class support for durability and availability, right? So we needed a good starting point to start building the system, and we need to study the existing solutions, what they're doing right, what they're doing wrong. Can we just adopt one, or do we really need to re-architect things? So a very obvious choice was to start with Flink. And next few slides will talk about architecture of Flink in a way that it makes it clear that any stream processing will dumb down to the essentials that Flink has embodied in its architecture, right? So let's dig into what Flink is exactly doing and how we have adopted it. So this is a famous diagram. Like if you want to understand Flink's architecture, this is what shows up. And this breaks down the entire system into three core components, right? So you have a client layer, like the one on the left, which says Flink program. And then you have a job management layer at the bottom. And then you have a worker layer, which is at the top, right? And if you spend time with any streaming system, this kind of a hierarchy will naturally emerge, right? So let's break this entire architecture down into the three key steps, the three main things that are happening here. So the very first thing is having a planning layer, a client planning layer, where you convert the program code into a logical graph. Now, why exactly do you need any kind of a logical graph, right? So like this is the scenario where there's some program code which is getting optimized by a graph builder, and then you basically, pass it forward along to some other component to work on. Let's look at this example. Like as a customer, I want to have a very simple pipeline. My data is in Kafka. I want to do a few operations on top of it, and then I want to push that data into Sync. Now here it's S3, but it can be Iceberg as well. Our system is architected in a way that it's Lakehouse native, right? So Sync can be anything. But if you look at any general scenario, you don't control how many operations a customer would want. Either there can be one operation or there can be thousands of them, right? And also you don't know what the source will be every time, what the sync will be every time. So you need a general enough data structure to encode the program code so that the rest of the system can operate on top of it. For example, like your system will not be specific to a certain pipeline that, hey, I can only do Kafka in S3 with one operator. You can't do that, right? You need to support n number of operators. So that's where this notion of logical graph comes in, which is built by the planner layer and sent to the job manager, right? We'll talk about what job manager does with it. But essentially what it does is captures the pipeline into a bunch of nodes and a bunch of edges, where a node is representing a unique ID for the operation, and it also encodes things like parallelism, right? So all of these things are hidden from the user, but they are essential in order to like build a state of the entire pipeline, actually run it, right? And edges capture the like data flow relation between all the operators. So the first step is doing that, right? And once you have one logical graph view of your pipeline, right, you need to have some running semantics on top of it, because this in itself has no notion of how it should be run, where it should be running, like in what parallelism it should be running. Like, of course, we have parallelism here, but there needs to be some notion of how to break it down into runnable components, which a job manager does. So for every logical graph that it obtains, it will assign a job ID to that, so that the entire system can always point to a particular pipeline, like it can map a pipeline to something running in the system. And then it breaks down one logical node into n tasks. So n will be your parallelism, and it will expand one logical edge to m task edges, right? And this will be an adaptive algorithm where you want to build edges based on what operations you have. So for example, in this specific program code, in operator 3, you're doing a key by, which essentially will shuffle your data between these different operators. So your task edges should basically encode this information. Like it should know that which operator and which operator task is sending data to which other operator task. Right? So if we specifically look at an example, like our Kafka source logical node will break down into two different tasks, where the first task has the parallelism index of 0, and the second one has a parallelism index of 1. Right? These are representative, of course, they will have more information. And here if you see the configuration for these two different tasks also encode what partition we want to read from. So in a way, this entire task is self-contained. You can give it to any system, any worker, like which we'll see downstream, and then it can basically run it. Like, so this is how you break down a node, and then similarly you will expand the edge. So in this scenario, you have an edge going from Kafka to a filter operation, right? But you see there is a partitioning of rebalance, and this is because if you go here, right, so it's not guaranteed that you want to run every operator at same parallelism level. You would want to run an operation which is very compute heavy at a very high parallelism, right? So in that scenario, if the parallelism of all of the nodes do not match, then you need to do something like this, where you have to rebalance the data. So when this expansion happens, your first Kafka node is passing data to first Kafka task is passing data to the first filter task, right? And then the second Kafka task is also passing data to the first filter task. So you have to basically create this relation between how do you send data, and downstream you have to make sure that you're splitting data when you're sending data to different downstream tasks, right? So in this scenario, it's mapped from 0 to 0, 1 to 0, 0 to 1, and then in the end, like to the third filter task as well, right? So this breakdown is important. And once this view, this self-contained task and logical and edge expansion is done, right, the job does not end there. Now you have to find some worker downstream which is actually compatible with this expansion that you have done. You have to find a worker which can run your pipeline, which has the resources to do it, right? So this means you have to have a view of all the workers, so all that state management needs to be there. And then you have to assign this job, and then you have to split it between different workers. So this requires the job management layer to be aware of capacity, like, and how the resource management is happening at the workers. And then this layer, right, the job management layer should also be aware of any reconciliations to be made, any checkpoints to be triggered. It also checks for heartbeats and any kind of rescaling that you need to do. Let's say if you pause your pipeline and you want to scale it down, right? So this is also something. This also requires some component, some layer, which is essentially a job management layer. So, in essence, we naturally arrived that with a need of a job management layer, which actually converts the graph into runnable components and then actually distributes it between the downstream workers and then also manages all of them with like a coherent view of a job. Now, the core part of it, like the thing that actually runs it, is a worker, which Arush will talk about.
Yeah, so now I think all of us know what a job graph is. And now the next core component that handles the rest of the things is a worker. Worker starts off with a task manager. Think of task manager as the actual container. It's the actual execution environment for running the tasks. The task is essentially an operator. Operator is the actual running entity, which is the actual thing that utilizes resources. So the task manager is resource aware. It knows about the architecture, the components. It is the thing that has to do the memory management, the IO management, network buffers, managing network IO, and the actual task slots where these operator instances would be running. So an operator is essentially the smallest unit of task which would take in some data, do some internal logic on top of it, and pass that information to our downstream operators. So our pipeline is having a source, then having many number of operators. Operators are connected by channels, and then eventually we send the data to a durable persistent state store. So these are some of the lifecycle methods that an operator has, and every operator has its own implementation of these operators. So start would be telling the operator to start its job, process messages, taking the message from an upstream operator, doing the logic and passing it downstream. Process checkpoint is something that is done regularly within a defined interval, as in when the operator receives a process checkpoint thing, it has to pass the data to a persistent state store. Uh, every operator has its own buffers. It needs to flush those buffers. And process commit is committing the changes. It can have many use cases. On close is freeing up the resources and stopping the network connections. Again, operator can still have buffers, so whatever is that is there in the buffer needs to be flushed to somewhere. And then yeah, this is how the data flow is between operators. So operators would have collectors, then the actual job graph would tell it to what exactly it needs to be passed on. We have our methods and implementations, all of those things. And then this particularly interesting concept of operator chaining. It's a core implementation detail, but I think it's very interesting to talk about. So operator chaining is saving overhead in terms of IO. How do we do it? Is, say, on a single node, you have multiple operators running, and since we're on the same node, we don't have to. As in, we can save time with in terms of serializing and deserializing data between operators. So this is something that the worker handles. We chain these operators, and then it's eventually passing the information to the first operator, and then without having the hassle of serializing and deserializing data, we the job graph is prepared in such a way that all the operators essentially work on the same data without having to deserialize and serialize data. And now what we are essentially trying to do is implementing all of this in Rust. So you all know, you all have been in the dev world, you would know the JVM overhead, how much of pain it is in terms of performance. So Rust has a very good runtime scheduler, Tokyo, which allows for very fine-grained resource allocation, and also that one thread doesn't need to run only one task. We can run multiple tasks async or synchronously within a thread. So Rust allows us to eliminate the JVM overhead, which is pretty much not having to use a garbage collector. So just for a slight context, Rust has this concept of borrowing and ownership, which is you won't end up with dangling data references. If the data needs to be passed, the calling entity needs to have ownership of data, or you need to mention that it is borrowing data. If there's no owner for particular data, it gets lost. As in, there's no need for a garbage collector to remove those dangling references. And then what we're trying to do is have a tighter integration with other E6 data compute engines. So that allows us to have better control over things and fine tune the bells and whistles ourselves, which is why we are interested in making a stream processing engine for ourselves. Okay, next are results. I think now we can talk about those.
So before moving on to results, just quickly summarizing on a high level what what we have achieved so far is that we basically took Flink as an inspiration and broke it down into the core components that any stream processing engine would have, right? And then we essentially rebuilt all of that in Rust because we realized for the workloads that we want to run, the core problem to solve is scale. And as we saw, right, like the existing stream processing solutions are costly. So doing as less compute as possible while still maintaining the expressivity of operators, sync sources, declarative pipelines required us to build all of this. So we did that in Rust. So very initial results were super promising in the sense that they at least match the performance of existing systems like Flink, while still giving us tighter control because you are aware fully of the code base. So a very initial run, like this is a snippet from a CLI tool we built to just constantly evaluate our dev cycle, like what's the performance, what we're doing. So in this kind of a test configuration, for one CPU, we were able to process about like 600K records per second, like every record being 1 kilobyte. And the fact that we built this notion of operators and this logical graph and all of this allows us to also somewhat linearly scale as the number of CPUs increase, right? So this basically allows for the entire system to be highly elastic in the sense that if you have a scenario where your stream does not process a lot of data, just you can use just one CPU and be done with it. You can just pay the cost of one CPU and run the entire stream processing at a very lower throughput rate. But let's say if you want to process millions of records, feel free to throw 64 CPUs, a big beefy machine, and the stream processing engine will adapt to that, right? So we saw linear growth and we saw good enough performance per CPU, right? So that was promising. Like the key takeaways for us as a team was realizing that stream processing is very hard topic, right? And Flink is an engineering marvel, and I think over time it has to stick with the ways it was built, and maybe you can adopt the core principles while building a better version of it, right? Which we did. And another takeaway was while researching and understanding the space was that it's a very exciting space. Like so many options are emerging out, and I feel like all of them capture this essence that we can do stream processing much better, like as a community. So like a lot of mechanical sympathy was built through this process, right? We're still in the process of evolving the system, building more connectors. We have first class support for Iceberg, right? But we want to expand it to other lake houses as well. So if you would want to join us in this mission, please scan this, and we're happy to talk about this. Thank you.